Topic 7 is on equilibrium. So we did cover this sophomore year. If you recall the Chatelier's principle, this is essentially what the unit is about. Chemical equilibrium in a closed system, a state in which the rates of the forward and reverse reactions are equal. So here you can see a reaction where nitrogen gas and hydrogen gas react to form ammonia. The reverse reaction would be ammonia breaking apart back into nitrogen gas and hydrogen gas. Instead of writing both the forward and the reverse reactions separately, we can write them as one reaction with a double-sided arrow. Characteristics of chemical and physical systems in equilibrium. Most chemical reactions do not go to completion once products are formed. The reverse reaction can take place to reform the reactants. In a closed system containing water, equilibrium can be reached between liquid, water, and water vapor. So here is a diagram that illustrates that. So you start with solid ice, and when it hits the melting point, it melts. And this is the whole time while it's melting. Now it's at the liquid phase, so this entire time it's liquid phase until it reaches the point of evaporation or the boiling point, in which case then it's evaporating. And then once it's all evaporated and it turns into gas, then it goes into the gas state. Okay, so remember that this is the heat of fusion. Fusion is another word for melting. Heat of vaporization would be the when it's evaporating. And if you were to go in the backwards direction, reverse direction, so the gas going back to a liquid, that is called condensation. And then the liquid going back to a solid, that's called freezing. You need to know, this is some new information. The reaction quotient, represented by capital Q, is going to be the concentration of the products divided by the concentration of the reactant. So remember that that's what these square brackets mean. These square brackets mean the concentration of. So the concentration of the products divided by the concentration of the reactants. So this value changes as the reaction proceeds. Once it reaches equilibrium, then it's called the equilibrium constant, Kc. So Q is the reaction quotient at any time during the reaction, but once it reaches equilibrium, it is called the equilibrium constant, and it's represented by K with a subscript C. And so this is equilibrium law states that Kc is the equilibrium constant, which is the value of the constant when a reaction reaches equilibrium. To deduce Kc from an equation for a homogeneous reaction, this is the formula that you use. Notice it's exactly the same as Q, the reaction quotient. It's just this one represents specifically at equilibrium. And so it's still going to be found by taking the concentration of the products divided by the concentration of the reactants. So here you have an example, the equation for the main reaction in the Haber process. We'll talk more about the Haber process next year. Is again, nitrogen gas reacting with hydrogen gas to form ammonia. In this case, the delta H value is negative. You guys should know what that means. A negative delta H means what? That it's exothermic. Good. So now you would write the equilibrium constant expression Kc for the production of ammonium. So that would be the concentration of the product, which is NH3, and then you would divide it by the concentration of both of the reactants. So I'm going to show you how you write that and add it to your notes. So this is how you would write the Kc value. Notice that I have the products in the numerator. There's only one product for this one, which is NH3. It's the concentration of NH3. The exponent 2 comes from the coefficient of the balanced equation. So the 2 coefficient is where the exponent 2 comes from in the equilibrium expression right here. And then in the denominator, notice that I put both of the reactants, N2 and H2. They're being multiplied. Okay, you guys know that this when they're just right next to each other. That means they're being multiplied. And the exponent of this one is 1 because the coefficient is 1 in the balanced equation. And the exponent of this one is 3 because the coefficient is 3 in the balanced equation. We will be looking at this next year. Determine relationships for different KCs at same temperatures. If given data, possible reasons for differences. So we're going to be looking at that more in detail. That's one of the skills that you need to do for this topic. You also need to know the magnitude of the equilibrium constant. So if a reaction goes nearly to completion, then you're going to be able to deduce that the Kc value was larger than 1. Whereas if a reaction doesn't proceed very much, in other words, it's a very non-spontaneous process, then the Kc value would be less than 1. And then this brings us to a review of what we learned last year, Le Chatelier's principle. So this was the main thing that we learned about equilibrium last year. If a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. Solids and liquids do not have an effect on equilibrium. So that is something new that we're adding that we didn't have last year. So the first factor that affects equilibrium is changing the concentration. For example, if you add reactants, then the equilibrium is going to shift to the opposite side, which is going to be to the product side. If you were to add more of the products, then it would shift to the reactant side, again, to the opposite side. So add opposite, if you guys remember that from last year, add opposite. Now, if you remove or subtract reactants, then it's going to shift to the same side, which is the reactants. If you were to subtract or remove products, then it would shift to the same side, which is the products. So subtract, same. So one more time. Add opposite, subtract, same. Here's an example. So we have this reaction, and if we were to add more carbon monoxide, then it would shift to the opposite side, so it would shift to the right. If we were to remove hydrogen, it would leave an empty space here, and so it would shift to that same side, to the reactant side, in order to fill up that hole. The second thing that can affect equilibrium is changing the volume, aka changing the pressure. Remember that these two things kind of go together, but they have an inverse relationship. Increasing the volume is the same as decreasing the pressure, or vice versa. If you decrease the volume, it's the same as increasing the pressure. Remember, they have an inverse relationship. So if you were to increase the volume on this reaction, it would cause a shift to the side with more moles. So you need to look at both sides of the reaction. You have to see how many moles of stuff there is. For example, there's only 1 mole of carbon monoxide and 3 moles of hydrogen. If you add those up, there's a total of 4 moles of reactants. On the product side, you have 1 mole of CH4 and 1 mole of water. Add those up, you have a total of 2 moles of products. So the side that has more moles, that's the side that the equilibrium is going to shift to if you increase the volume, aka decrease the pressure. Remember, it's the same thing. So increasing the volume for this reaction would shift to the side with more moles, which is the left. Okay? If there was an equal number of moles, then there would be no shift, and we do have an example for that. Now, if you do the opposite, if you decrease the volume, which is increased in the pressure, now it's going to shift to the side that has less moles. So again, same reaction. This has 4 moles. The product side has 2 moles. If you decrease the volume, it's going to increase the amount of collisions. Therefore, you're going to see a shift to the side that has less moles. So it's going to be to the right side. So here's an example where you have 1 plus 1, 2 moles of reactants and 2 moles of products. Since there are 2 moles on each side, then changing the volume would cause no shift at all. Whether you increase or decrease the volume, there would be no shift. The third factor that can affect equilibrium is temperature. So for this one, you have to pay attention to whether it's an exothermic or an endothermic reaction. So you have to look at where the heat is located. So here you see that the heat is on the product side. If heat is on the product side, that means heat is being released. Therefore, you can deduce that it's an exothermic reaction. This in parentheses are all the different units you might see of heat: joules, kilojoules, calories, and kilocalories. So if there's heat released, it's going to be an exothermic reaction. So then you go back to the same rules that we talked about when changing the concentration. If you add heat, which is the same thing as increasing the temperature, in an exothermic reaction, adding heat is going to shift to the opposite side. So add opposite. And if you subtract heat, which is the same thing as decreasing the temperature, remove heat, then it's going to shift to the same side, which is the products. That's for exothermic. Now it changes for endothermic because, of course, in an endothermic reaction, you're going to require heat, and that means that the heat is going to be over here on the reactant side. Therefore, the rules are the same, but now the heat is on the other side. So if you were to add heat to an endothermic reaction, it's going to shift to the opposite side, which is products. If you remove heat, then it's going to shift to the same side, which is the reactants. Okay, so a couple things to note: that if you were to change the temperature of a reaction, then it is going to change the value of Kc. Again, we're going to focus more on Kc later, but you know the general idea of how to plug it into that formula that I showed you. And adding a catalyst is not going to affect Kc. Because adding a catalyst is going to speed up both the forward and the reverse reaction rate, so they end up canceling out. But changing the temperature is going to change the value of Kc. And that's topic 7.